Hi, today we're going to take a look at hypothesis testing. We're going to introduce this idea. And the video, like the starting bit to this video, is actually inspired by a video by Khan Academy. And they have these little selection of people. So I kind of wanted to create it along the same lines, almost to pay homage to it, but because it's such a good explanation, I'm going to do it in my own way, but definitely taking on board aspects that they say. So first of all, a hypothesis is an initial explanation for an observation that can be tested by further investigation. You might have a hypothesis that perhaps in a detective kind of series, and you think like this could be the case, and then you try and gather evidence to prove it or disprove it. And what we're going to look at here is along similar lines. So let's imagine we've got four siblings, and they've got to choose a rota for who does the washing up. And what they decide is that they're just going to pick their name out of a hat each time. They're not just going to go and do it alternately. They're going to have a bit of probability in there. So their names are going to go into a hat, and then whoever's name comes out does the washing up. Now, let's say the older brother, and we'll call him Bill. They do that in the Khan Academy video. Okay, he's going to sort of set this up and then pick the names out. But what actually then happens is that Bill himself doesn't get chosen for the next five times that they're washing up, and the other three are thinking, is that right? Is Bill kind of rigging the system here, or is everything actually fine? And so they look at their probability and they think, what was the probability that in five amounts of washing up, Bill's not actually doing it at all. And if we were to draw our tree diagram, Bill doing the washing up or not, we could actually do lots of branches. Okay, this is Bill not doing the washing up. And it would obviously these would branch out more, you get lots of branches, but Bill not doing the washing up would be all the way along here. And actually there's a 0.75 chance of him not doing the washing up. So for n equals 5, for 5 times, the probability that he wouldn't do the washing up would be 0.75 to the power of 5. And we can put that into our calculator, and actually it gives us 0.237 or 24%. So it's not that low a probability that he wouldn't have been picked after 5 goes. So maybe they're happy, they think, okay, that's just chance, and he's not had it, but there was a 1 in 4 chance that wouldn't have happened. Okay, let's say though that after 10 goes, he still hasn't had a turn at washing up. His name's not come out the hat once. And now they're getting really suspicious. They're thinking, can this really be the case that he's not been picked after 10 times? And the probability of this happening, if we again look at our tree diagram, which is, by the way, an example of a binomial distribution, the fact that we're just getting 10 successes or failures, depending on how you look at it. It would be 10 successes that he's not doing the washing up. So it would be a success for him. It's actually 0.0568. So now we're getting to around 5%, and that does seem to be suspicious. There is a chance, 1 in every 20 of that lot, he wouldn't get, you might expect him to not be picked, but, you're kind of thinking that it should have happened by now. And if we take it further, let's say after 20 goes, he's not been picked. Okay, that is now, well, we're going to end up squaring our last result, and that's going to be really small. So if he hasn't been picked after 20 goes, you'd definitely be mega suspicious because it's 0.00317, which is actually going to be 0.3%. Okay, and this brings us to the idea of hypothesis testing. So what might the hypothesis be? It might be that these three construct the hypothesis that Bill he's rigging the system. He is, he's not actually doing it fairly. He's not doing any washing up. It can't just be chance that that's happening, especially since he designed the system. So they're going to have that as a hypothesis, and then they're going to maybe test it. They might they might have come up with this hypothesis at this point here, and then they might have said, right, well, now we're going to look at the next 10 times that the name comes up, and if the probability, if it doesn't happen again, the probability of it happening is low enough, then we've got evidence that actually he's rigging the system. So they've got a hypothesis, they've decided how many goes to how many tries, and then they might say, well, if there's a less than a 5% chance of it happening, then we're going to say that it definitely, surely we're going to accept our hypothesis that he is cheating. Or maybe in this case, it couldn't have been less than 5%, but maybe they try it for 20 times, okay? Maybe they say, what's the probability of it happening? If the probability of however many times he washes up is less than 5%, then we're definitely going to accept our hypothesis. And this is basically what we're doing in hypothesis testing, but we write it a bit more formally. Okay, so I'm now going to show you how we would actually set it out. So this is what happens, okay, because the terminology gets quite technical, but there's just a few terms to be aware of. So when we have this kind of hypothesis testing, what we do is we construct a null hypothesis. And we say that, okay, this is the case in which everything's actually fair, and the probability that Bill is being picked is 0.25. There's a 1 in 4 chance. P is equal to 0.25. Because then we can actually use this because with that fixed probability, we can make some calculations. We then have a different hypothesis, which we call an alternative hypothesis. We call this H0 and this one H1. And that is our suspicion. The probability that Bill is picked is actually less than 0.25. Okay, we can't really do a calculation with that because we don't actually know what it is. We want to test. We want to kind of convince ourselves that that is the case or find out if it is. Okay, so these are two absolutely crucial ideas. So when we construct a hypothesis, actually we construct two hypotheses, a null and an alternative. What do we do then? Now we assume that the null hypothesis is true. Like I said before, that's the one we can do calculations for. So we're going to assume that's true and we're going to investigate it. And then you look at some amounts of, you take a sample of the net of something. So in this case, you might look at the next 20 people selected to do the washing up. I've just chosen 20 here. That's why I've written it in red. You might choose the next 50. You might choose the next 5. The issue with 5 is that there's a good chance that he might not be picked. So you need your sample, or however many you're looking at, to be reasonably large. Okay? And then let's say that Bill only gets selected in one of these. So actually, if he is rigging it, he's probably not going to, make it so he never does it. He's just going to subtly just put his name out there sometime so that it looks like he actually can be picked. But what's the probability that he was just picked once or less than once in 20? That's still going to be quite small. We're going to find a probability that this would happen, basically, this many or fewer times. We don't just look at the probability that he's picked once, we actually look at the probability that he's picked once or less, because we need to look at basically the cumulative distribution. Okay, what we then do is we construct a test statistic. So X is going to be the number of times that Bill is selected. So here's another keyword. It's called the test statistic. It's the thing that we're testing using statistics. But this is something we do every time for these hypothesis tests. I'm trying to link it into what I talked about before, but write it down more formally. And then this is the key bit. We do our calculation. We're going to assume that X follows a binomial distribution. There are 20 trials. There is a fixed number of trials. The probability of success is 0.25. We've got a binomial distribution. We have to assume that the events are independent, that one does not affect the other. And we also have to assume for this fixed probability. And then we're going to test the hypothesis, the hypotheses, I should say, at the 5% significance level. So this is me saying, this is like I was saying before, we want to be kind of really sure, like, there's got to be a less than 5% chance that it could have happened just randomly due to natural variation. So we decide a level. And if you want to be really sure, you would reduce the significance level, maybe to 1%. That's why I've written this in red. It's not 5% every time. If you want to be like reasonably confident, you might make it 10%. If you want to be pretty confident, 5%. Very confident, 1%. Extremely confident, maybe use a 0.1% or 0.5% significance level. So it's kind of your testing amounts, how confident you want to be. Okay, and then what we do is we do a calculation. So the probability that x is less than or equal to 1. We know that he has only been selected once, so we find the probability he selected once or less, and that turns out to be 2.43%. That is the probability that that possibly could have happened. He either is selected 0 times or selected 1 time. And we call this the actual significance level. Like I said, it's that probability that it would have happened. So there's a 2.43% probability that it would have happened through chance. And remember, our level that we're interested in is 5%. So we compare these and we say, actually, we would have accepted it if it was above 5% because there would have been a good enough chance of it happening randomly. But actually, it's less than 5%. It's less than our level that we've set. So it cannot be that it's happened at random chance. It cannot be actually that H0 was true. So we say that we reject H0, the null hypothesis. It is statistically significant that H1 is true, i.e. it's likely to have occurred, it's unlikely to have occurred by chance. And therefore we make a conclusion in context. We conclude that Bill actually has a less than 25% chance of being picked. He may have rigged the system, okay? That's our suspicion. He might argue. Otherwise, he might say, oh, I accidentally didn't put my name in the hat, or, on some occasions I didn't mean to, but somehow it's ended up in his favor. And if you understand that, you've understood the main idea behind hypothesis testing. I'm just going to summarize. We get a null and an alternative hypothesis. The null one is the one that we can actually test. We then assume that it's true, and we're going to construct a test statistic which follows some sort of distribution. We're looking at binomial here. You can look at other distributions, but we've been studying binomial. We're going to start with that. And then we test it at a significance level of some choosing. Okay, we work out the probability of it happening, the events happening that actually has happened, and we compare them, and then we can either reject or accept H0, and then we can make a conclusion. Okay, so we have introduced the idea of hypothesis testing and all this different terminology. So just take a look here. The number of times Bill was selected was the test statistic in that case, and we had a null hypothesis that Bill was picked as 0.25, an alternative that it was less than 0.25 the probability. So we're going to look at three other situations, and I want you to think about what H0, H1, and the test statistic could be. So pause the video at suitable points and try this first one now. Okay, for this first one, the null hypothesis is going to actually be that the dice is fair, that actually there is a 1 in 6 chance of us rolling a 1, because that's the one we can then test. So H1 is then going to be that P is greater than 1 in 6, because in this case, we think that it's biased towards the value of 1. So you've got to just be careful and read in the question, so that will tell you about your alternative hypothesis. For Bill, it was less than 0.25 because we thought he wasn't being picked as much as he should have. Here we think 1 is actually coming up more than it should. So just be careful with that. And then the test statistic is going to be the number of 1s rolled. That's what we're going to actually find the probability for. That's what we could measure if it was thrown 60 times. Next one. Here we've got a manufacturing process, and we think from long experience the probability of it being faulty is 0.1. We're going to take a sample and see if there's been a reduction in the proportion of faulty items. So H0 here is going to be P is equal to 0.1. It's the one we had before, the thing that we can actually test. Now we're interested in whether there's been a reduction, so this time P is going to be less than 0.1 for the alternative hypothesis. That's the probability of an item being faulty. And then finally, the test statistic, what can we actually measure? It's going to be the number of faulty items. So that's the thing we can then calculate using a binomial distribution. And finally, we've got a polls, 55% voters support a candidate, but then we've got some scandal happening. And following that, they want to know whether they still support the candidate or not. So H0 is going to be that P is 0.55, that we still have this 0.55, but we're going to be interested in whether now less people support the candidate. That's not actually quite as clear in this information, but you can kind of see where it's coming from in the question. Yeah, it's going to be less than. So P is less than 0.55. And then what can we actually measure? The number of people who support the candidates. Okay, here is the full thing then from scratch. This is the sort of question we get for hypothesis testing. Travel company finds from its records that 40% of its customers, I'm just going to underline that, that's going to be a key thing, book with travel agents. The company redesigns its website and then carries out a survey of 10 randomly chosen customers. The result is that 1 books with a travel agent. Test at the 5% significance level whether the percentage of customers who book with travel agents has decreased. All right, so I think the first thing to do is write down our null hypothesis. H0 that P is going to equal 0.4, i.e. it's not changed, it's still 40%, because that's the thing we could do calculations with. You don't have to define all of these things, it's enough to say that it will be implied that we know what we're doing here. And then we're interested in whether that amount has decreased. So it's the alternative hypothesis is going to be that P is less than 0.4. So let X be, now we need to talk about the test statistic. And what is the test statistic going to be? What's the thing we can measure? The number of customers who booked with the travel agent, but we see that we've had 10 picks. So let X be the number of people, you could say out of 10, but again, it's implied, who booked with a travel agent. Okay, you should write that down just to make it clear. And then what do? We assume H0 is true because that allows us to do a calculation. And that means that X will follow a binomial distribution. We can see that we're doing 10 trials and the probability of success is 0.4. Now I can only write this down because H0 is true, because I've assumed it's true, so the probability is 0.4. All right, and now we've seen that the actual result is that one of these customers booked with a travel agent. So what we have to do is work out the probability that that would have happened. But we don't just look at the probability that it's just 1, it's going to be 1 or less. Because imagine you had like 500 randomly chosen customers. The probability is going to depend on your sample size for it to be 1. And as the sample becomes bigger, the probability of it getting 1 customer is going to decrease. But we're more interested in the probability. That's why we need to look at the probability it's going to be 1 or less. Because let's say it was 100 people booked with a travel agent. That for 500 people is still going to be a small probability, but 100 or less is going to be much bigger. I'm just trying to explain why you always look at the cumulative. Okay, and then we can figure that out. But for this one, we're going to actually have to use our calculator and get the answer. So I'm going to look at my distribution function. Sorry, my binomial function, my binomial CD function, and then I just need this one variable. Although I think I'm going to get the list out just to compare. Okay, I'm actually only interested in 1, but just for comparisons, I'm going to show some more. And then I've got n is equal to 10, P is equal to 0.4. And I see that actually the probability of X is less than or equal to 1 is 0.0463. Which is 4.63%. So actually, that is the chance that could have happened through pure chance, essentially. And I can write down, do you know what? I can even write it down here. I can write down that this is less than 5%. Okay, so there is a smaller chance of it happening at random than we've accepted, this accepted level. This, remember, is called the actual significance. This is 4.63. But what it means, because it's less than it, is that we're actually going to reject H naught. Okay, actually, there's a smaller chance than we've accepted of it happening through natural variation. So it can't be that H naught was true. We tend to write reject H naught or accept H naught. You could, of course, say accept H1, but if we rejected H naught, we should then just write a conclusion. The percentage of customers who book with travel agents has decreased. Okay, so don't rush these questions. These are all the lines that should be there. You can add extra if you want. You can define what P is. But yes, we need to have these hypotheses. I would like to see the test statistic. We need to say that H naught is true. Therefore, it's going to follow some sort of distribution, in this case binomial. Work out the probability of the situation happening. Compare it with the significance level. Reject or accept, and then write a conclusion with context. That's the way to go. Okay, just the last little bit of the question. I think I'm running out of now. I've got a bit of space here. So the managing director says that our redesigned website has resulted in a decrease in the percentage of our customers who booked with travel agents. Comment on this statement. Well, the fact is that there has been a decrease in the percentage. And actually, we've accepted H1 in this case. We've said that it has gone down and it's statistically significant. However, the manager isn't just saying that; they're saying their redesigned website has resulted in it. And the key thing is that we don't know that. Okay, we cannot. It's a bit like causation. Correlation does not imply causation. Just because you get a good correlation doesn't mean that one actually affects the other one. We cannot assume cause and effect. Okay, there might be other reasons why it's gone down. So we basically, you can't put that on you can't make that claim. All right, have a go at this question now. Actually, this question, you might have thought, well, is this really useful related to washing up and, I don't know, travel companies? But this is, a clear application of hypothesis testing. When treatments are being made for diseases or medicine is given out, then we have to look at the amount of success and failure. And you can't just imagine that, something's always going to work. So we look for it to be statistically significant. This is exactly the sort of thing that is going on all the time in, say, the pharmaceutical industry. We need to get enough evidence of it happening, so we can use hypothesis testing to do that. So this is a fantastic question to show this application. Okay, hopefully you've had a go at it. So a suitable null and alternative hypotheses. It's going to be that the probability is 2/5. Right, so we can do calculations with that one. And then because we're interested in an improvement in the standard treatment, then H1 is going to be that P is greater than 2/5 this time. Okay, then to write down the distribution of the random variable X, they've already told us what that is, this test statistic, the number of patients that would be cured if the null hypothesis were true. That's going to follow a binomial distribution with our 20 trials, because you can see that's how many they've done, and then the probability of success follows our null hypothesis 2 over 5. If we then want to work out the probability of x taking a value equal to or greater than 11, it's guiding us through here. That's what we need to do to work out whether this is statistically significant, that we managed to get 11 out of 20 success. So we can work that out, and it turns out to be 12.75%. Just a little reminder about that, I think it's worth doing. So remember, it's distribution. It would be binomial CD, and then we would do variable potentially, and then to work this out, it would be 1 minus the probability that x is less than or equal to 10. Okay, we don't have this cumulative distribution for greater than, we've got it for less than, so we just have to basically do 1 and then subtract all the values from 0 up to 10. That will leave us 11 and above. So if we look at our 20 trials, and then the probability is 2 over 5, which is 0.4, then we get 0.8724, okay, but we need to do 1 minus that, and there we have it, 12.75%. Just a reminder about that. All right, so if the significance level is to be 5%, does 11 patients out of 20 provide enough evidence to reject H0? And in this case, the answer is no. There's actually almost a 13% chance that this could have happened through natural variation just by luck. So it doesn't meet our demands. Actually, there's not enough evidence to reject H0, and you would say, except H0, the new drug is no better than the old one. Of course, we might need to do, more trials. Yeah, maybe you'd say at this level of significance and with this evidence, the new drug is no better than the old one. But we have to make a conclusion at the end of the day. So we've seen in this video an introduction to hypothesis testing. I've formalized it and gone through it and introduced this terminology. Okay, we'll talk about these again in future lessons. The actual significance level has only just kind of cropped up today a little bit. And then we've looked at some test statistics and null hypotheses. We've looked at a full-on example from scratch, whereas this is the sort of thing you should be writing down. Just be careful when actually it comes to working out the probability. Do you want it to be less than or equal to or greater or equal to? You then make the comparison with the significance level. You're getting it to be less than the significance level to reject H0. If it's more than it, you're going to be accepting H0. Give context at the end of the question, and then just think about some of these questions, like whether you have cause and effect. So hopefully you are happy with that and you're ready to practice this a bit more. Thank you.